Hello there. We're going to look at Balmer lines today and absorption spectra, and we're going to look at this little table that's taken directly from the specification with spectral classes and temperatures and prominent absorption lines. So I'll do this little presentation. Hopefully, it will make some sense, and then we can build on that after that. I thought I'd start with some more mnemonics, which are maybe little bit nicer. So the spectral classes O, B, A, F, G, K, M, and you can use either of these if you want to. This all you need to remember is that O. Once you've got this order in place, the O is the hottest star, which will be your blue star, and M are your coolest stars, which is your red stars. So the idea that it's the opposite way to taps, so blue is hot for stars and red is cold, and also that we're looking at surface temperature, not the temperature in the core. That's millions of degrees C. So the range for the Hertzsprung-Russell diagram, of course, 2500 Kelvin up to 50,000 Kelvin. Okay. So here's what the stars look like with the different spectral classes if you were to take the visible light from it and split it up. So in terms of how bright the colour is, gives you an idea of the intensity of that frequency of light. You can notice the O-class star is very bright on the left-hand side of this diagram, so around the blues. And then your M-class star, very dim around the blues and very bright around the reds. So it should be clear that even though you can change the contrast on this, you can change the brightness. So if you wanted to see the blue light on an M-class star, it's there, and you can just make the screen brighter. But this is just to show that the red is much more prominent. So this, your eye, if you look at an M-class star, your eye will be picking up plenty of blue light, but a whole lot more yellow and green, and a whole heap more red. So it ends up looking red because there's so much more red than the other colours. And your K-class star, you can see that the brightest point starts to move over a little bit. So a K-class star would be an orange star, and then your G-class star tends to be more the yellowy stars, which is where our sun is. Then as we go up, you can see the F-class star is what we would consider a white star, because the green is the prominent colour. You can notice how the green is much brighter than anywhere above it or below it, and it's got just as much kind of yellow as the light blue here. So because you're getting an equal span to the left and to the right of the green, it ends up just having a nice mix of all the colours, which makes something look white. So the A, the B, and the O-class stars would just simply be called blue. I suppose A-class star often called a blue-white star. So white with a bluey tinge, which this would be blue, white with a yellowy tinge sometimes, but then this is just plain blue, these blue stars. Okay, so that's the colour, but that's breaking it down into the visible spectrum and showing you that that it's not a yellow star is not just yellow light. It's just more prominent in the yellow light. So that's discussing the prominence of the actual frequencies that we can see. The next thing we need to do is maybe a little bit more profound. It's looking at what isn't there. It's looking at the prominence of these black lines, what would be referred to as absorption lines. So you can see that they're all a bit different. The lines appear in the same place. So this line here, you can see the lines coming through. It's in the same place for everything because it's the same element. But if you pick a particular line, it will be darker in a certain spectral class. This line here is darker around here or here, isn't it? This line here is clearly much darker here. And you can pick one that's darker up here, darker around here, and but there's a whole host of lines, and each one you could link it back to a element. Okay, so this is looking at it in a bit more detail. They've split the spectral classes into numbers, which you can do. You can split it, further categorize it, but we don't need to. And you can see, yeah, but we're starting to name them. Starting to name the lines here. So you can see anything with an H is your hydrogen, He is your helium, and you've got some iron lines here. So it's like a fingerprint for stars. We can see where the line is exactly. We can tell the frequency. We can see what element that is. Remember, it's absorbed. The light is absorbed by particular atoms which have specific energy levels which perfectly match the energy of the photon, and that would be done in your particles and radiation topic. So, and then it does get re-emitted. It gets re-emitted, but in a random direction, which is why we don't receive very much of it at all, but we do receive some of it. Okay, so the key ones here, this is H, and you can see there's a little Greek letter next to it. So the first one for hydrogen in the visible spectrum is known as H alpha. You can probably guess what the second hydrogen line is called, H beta. H gamma, H delta, that's how it goes. So yeah, they've just given the Greek letters to the absorption lines that lie in the visible spectrum. Now, I'm going to go on about hydrogen more than any other element because of this. This is showing that about 3/4 of the known universe is hydrogen and about 1/4 of it is helium. 1% is the heavier elements. That's it. So stars are mostly hydrogen, the universe is mostly hydrogen, the early universe was just 3 or 4 elements, It's a long time till the heavier elements got made, and anything heavier than iron can only be made in a supernova. So the reason that hydrogen is so important to astronomers is because it's so abundant in the universe. Now, this is the hydrogen absorption spectrum and the hydrogen emission spectrum, which you could have read for yourself. But these lines here, so if you have, imagine a star, so there's a light source which is emitting all the frequencies of visible light, and then you put hydrogen gas in the way. So you'd receive still all the frequencies, but there'd be a few gaps. And those gaps have been absorbed by the hydrogen gas. So this is when there's a light source far away from you, and then in between you and the light source you've got hydrogen gas. And the hydrogen gas has like stolen these particular frequencies. This is the other way around. This is just if you heat hydrogen gas, force it to excite and then de-excite and then emit these particular colours. So look, whether it's absorbing or emitting, the energy level gaps are still the same. So you're going to get the same frequencies. So absorption spectrum, emission spectrum, the lines match up exactly where they are. So this is where you just heat hydrogen gas. So we've got the first one, H alpha, H beta, H gamma, H delta. And here are the energy levels for hydrogen, and it's a misconception, I suppose, or we teach it in that way. In chemistry, you picture your little model of hydrogen. You've got your one proton in the nucleus, and then you've got a single ring, single shell, where you just put your single electron on. But that's not the only position where that electron can sit. So yes, there's a single electron, but it can exist in different states. It can exist in different energy levels. It can go up and down. It can excite and de-excite. But there is a finite amount of energy levels it can exist in. And here they are. So you have, this is often shown the other way around, I must add. You often put 0 at the top and then have negative values here. But you can have this way of doing the energies. But here's the ground state, what we'd refer to as the ground state. So it can excite up and then excite down from there. It can so excite and de-excite. But if it was here, then all you would get up to there and down from there. So you can drop down from there. You can drop down from there. These are pretty big drops, 12.8 electron volts, 13.2 electron volts, 13.1 electron volts. That's a big amount of energy. So E equals HF, so E is proportional to F, which means a big energy is a big frequency or a high frequency. So these high frequency ones are down the high frequency end towards the gamma end. So actually, these lines that will be caused by excitation and de-excitation of hydrogen from the ground state would be in the ultraviolet region. So these here, much smaller energies, you can see it, that's a drop of 3 electron volts, a drop of 2.9 electron volts. So these are much smaller, so smaller energy, smaller frequency, so less frequency than ultraviolet. So these are your visible light, and that's called the Balmer series. But you only get that from a starting point of n equals 2, not the ground state. And you've never come across anything where it doesn't start from the ground state, so that's what we have to discuss. As we go further up, smaller energies, so smaller frequencies, so bigger wavelengths, in other words, so this is more around the infrared region. Okay, another way to show that then down here. So if it's exciting up and then down from the ground state, this is what we're calling the Lyman series, very small wavelength, looking at ultraviolet. Here's the Balmer series, or the Balmer line, so that's when you have a starting point of n equals 2. And when you have a starting point of n equals 3, you're into the Passion series, which is in the infrared. So if I go back here, these lines are to do with the visible light spectrum, which is on Earth, the thing that we've always studied the most. And so these lines, the Balmer series, are known as Balmer lines, H alpha, H beta, H gamma, H delta. Really important to astronomers, Balmer lines. Alright, so so this is a way to classify the star without, if you don't already know its temperature. You can look for Balmer lines, I suppose, and you can see here, if we look for H alpha in the different classes of stars, F, G, K, M. So we can't really see many Balmer lines here. We can't see the H alpha until we get up here. So the A-class star is showing that it has the darkest Balmer lines there. H alpha, all of them, H beta, H gamma, H delta. So clearly we're not getting many there. And unless in the exam you would have to potentially state why that is. Why do we get lots of H alpha lines here and not in the M, K, G class stars? So if we go back here, it's simply to do with this ground state. For the electron to exist and rest and have its ground state at n equals 2, it has to be permanently excited. And that will only happen in a star with a very high temperature. So simply put, your M-class stars, your K-class stars, they are not hot enough to have electrons in hydrogen sitting at n equals 2. So a simple explanation would be that as the star gets hotter, the ground state for hydrogen goes from n equals 1 up to n equals 2. And if it gets to the very hottest stars, the O and the B class stars, then the ground state can actually be n equals 3. So that's probably something new to you, what the ground state, where electrons can change what the ground state is as the temperature increases. So we do not see many Balmer lines or any Balmer lines here for the M class and the K class star because it's not hot enough for electrons to exist at n equals 2 as its ground state. They can excite up, but they tend to excite up much higher up. Okay, so as we go higher up, you can see that these have the hydrogen lines, but then there's other lines that we're interested in as well, which can help us figure out what spectral class we're dealing with. Okay, so that's the hydrogen lines versus the temperature. So you can see here, these still exist, but this is typically much more here around the 10,000 Kelvin. Now we add in some other elements. So you can see that if we were to look at helium, ionized helium, you can read them off there. All the different elements will have different, they've all got their own specific absorption lines which appear in the exact same place for all of your spectral classes, but they're more prominent in some than others. So here's the helium. You can see the helium peaks here. much higher up. So if we go back here, we can find your helium here and your helium here. Very hard to spot, but you're looking down here and you can see some creeping in, I suppose. And then what have we got? We've got the silicon and iron was on a previous one, I think. So if we go back here, yeah, you can start picking them out. Okay, so helium lines, iron up here somewhere. Okay. So what we can say is, if you look at a star and you can see really prominent hydrogen lines, otherwise known as Balmer lines, the ones that are in the visible spectrum. This is all to do with the visible spectrum. Then you're going to say that it's probably around that temperature, and typically around an A-class star. If you're seeing really prominent helium lines, you're saying it's hotter, your B-class star maybe. If you're seeing your titanium oxide, we're looking at your M-class stars. And then, so basically it starts with your metals, and then as it gets hotter it goes to your ionized metals, and then we get to the hydrogen lines, and then above the hydrogen lines we start to get the helium. It's got to be even hotter to have helium starting at a higher ground state. And that all leads to this. That's the science and the theory behind this table here. So we said that 10,000 Kelvin was the A-class star. That's where you get most of the hydrogen lines, otherwise known as Balmer lines. Okay, so there it is, 7,500 to 11,000 Kelvin. There's not many times, I say just learn this from the specification, but this is a time when we just need to get our heads around this table and be able to be given a little bit of information and say what spectral class that star is. Okay, so the starting temperature is 2,500 Kelvin. We need to know that to be able to add the axes to a Hertzsprung-Russell diagram. So the first class, M, is therefore 2,500 to 3,500. Now I find that it's easier not to remember all the numbers, but just to remember the starting point and the finishing point. The starting point is 2,500 Kelvin and the finishing point is 50,000 Kelvin. And then you can remember the gaps. The first gap is 1,000, the second gap is 1,500. Then it's 1,000 and then it's 1,500 again. Okay, so the first four jumps, 1,000, 1,500, 1,000, 1,500. So we go from 2,500 to 3,500. That's the first class. Then a big jump of 1,500 up to 5,000. That's the second class. Then a little jump of 1,000 up to 6,000. That's the third class, G class. And then another 1,500. That's your F class. And then there's a random number to remember. You can just remember 11. That's the only random number really we have to remember. So from there you go up to 11,000. That's your A-class star. And then most people can normally remember that the next jump is the halfway point, 25,000 Kelvin. So that's your B-class star. And then 25,000 to 50,000, the last half of the temperatures, is your O-class star, your very hottest. Here's the colours. It's pretty much the rainbow, isn't it? Red, orange, yellow, green, blue, blue, blue. Let's forget about indigo and violet for now. But yeah, they put blue, white and yellow, white. But yeah, it's essentially the whitest of the blues, that one. But that's the only one with yellow in. You do need to know where our sun sits. Our sun sits just below the 6,000 Kelvin mark. So it's a G-class star. And then this is what we have tried to explain today. So here, if you said it had very prominent Balmer lines, then you'd be putting it at an A-class star. If you said it had metals, neutral metals, titanium oxide, then you'd be putting it around the K or the M-class star. And then if you said it had ionized metals, well, those are the hotter. So there's your F-class star. G is a bit of a mix. You do get some ionized, but you also get some neutral metals there. That's just a case of trying to remember that. As we go above hydrogen, you can just think, well, yeah, we still get some Balmer lines, but we go the next element up, which is helium. And then look at this one, some ionized helium there as well. So yeah, you get absorption lines from those. So this is all referring to the absorption lines that we can see in the visible spectrum that star is giving off. So this has covered absorption lines, absorption spectra. It's covered well, it's revised, I suppose, electron energy levels and E equals HF, which is really important for your particles and radiation topic. And then it's really made an attempt to cover this bit, this column down the right hand side. Because I know this has been covered when you've studied Hertzsprung-Russell diagrams, as would this have been, but this bit here. And if it came to it just the day before the exam, you hadn't got your head around it, it would be a case of just trying to remember where hydrogen sits, because that's the most common thing you'll be asked about. Hydrogen is most prominent around the A class star at around 10,000 Kelvin. Okay, I hope that was helpful for you. Thank you very much.